I would like to thank the organizers to give me the opportunity to present the G-CAV survey as a representative of the international collaboration, and in particular, this opportunity allows me to talk, to spend a few words about the PI of the survey, which is Mario Nonnino. And I think, as you know, Mario Nonnino passed away this July 21st, fighting a very aggressive form of leukemia. And so in less than 2 months, he passed away. So Mario was a key person of this survey. Mario conceived the survey, prepared UBs, reduced the data, extract catalogs. So there's a huge collaboration, but I think Mario is very important and crucial for this survey, and also I think for other surveys. Mario was also a big friend for us, and he was writing the survey paper, but so this kind of dreams has interrupted due to this thing. So now we are continuing the work of Mario, and we are completing the survey paper, and also preparing the next data release that I think will be the last one for this survey. Okay, so coming back to the topic of the survey, we know that galaxy clusters are the ideal test beds to investigate the galaxy formation and evolution. In particular, galaxy cluster forming from primordial perturbations constitute a privileged environment to study the growth of the cosmic structures and the cosmic cycle of baryons. Not only we can use galaxy clusters to investigate the interplay between the galaxy mass and the environmental processes to transform galaxy properties. In particular, focusing also not only on the cluster center, but also on the outskirts, we can investigate the interaction with the ICM, such as run pressure stripping, strangulation, or thermal evaporation, and so on, and also the galaxy-galaxy interactions. So to do that, we need a large sample of galaxies in a wide variety of environments, so in different mass ranges and also in different environments. And this respect, VISTA, VIRCAM in particular, VISTA with the very large field of view offers a unique opportunity to investigate a wide dynamic range in density from the center of the galaxy cluster, the high density in the center of galaxy clusters, to the lower density in the outer region of clusters. In these figures, you can see the simulated data from the Millennium simulation, and in particular from the galaxy, the catalogs from the Lucier Blazo in 2007. And you can see the data of the galaxy clusters covering a region of 30 per 30 megaparsec. That is the region that we can cover with the VISTA field of view. And in the lower panels, there are clusters at redshift 0.3, and in the higher panel are galaxy clusters at redshift 0.6. And the galaxies are marked by circles where the radius of the circle is proportional to the stellar mass of the galaxies, and the red galaxies are the center galaxies in the halo, while the blue symbols represent the satellite galaxies. So you can see that only with VISTA we can span a very large sample of environments. So the main aim of this survey, the main scientific aim of this survey, is to investigate the interplay, so the relative impacts between mass quenching and environmental quenching. But we also have a legacy science for this data, because the G-CAV areas and also the depth allow us to search for high-redshift quasars and cool dwarf, as well as to study infrared galaxy star counts and colors to be compared with the theoretical predictions. G-CAV observed a sample, is a second generation ESO public survey and observed 20 massive galaxy clusters at intermediate redshift, so in the range between 0.2 and 0.9. These observations cover a total of 38 square degrees in Y, J, and KS bands. And as you can see in this plot, this is the distribution of the cluster sample as a function of the masses of the cluster samples as a function of the redshift. And for this data, we also have optical coverage from Subaru and also from VST data. And in magenta squares are the clusters observed with VST GTO survey, and with the blue squares are the Subaru data. Not only ground-based observations, but also we have a space of multi-band observations. I will come back on the ancillary data of the G-CAV samples in the next slides. So this sample will also, this sample is also contains also merging clusters. And merging clusters are an ideal laboratories to study the evolving galaxies, and in particular the turbulence and the shocks will change the star formation of galaxies, bursting the star formation in galaxies, or also going very, very fast to a transformation in passive galaxies. So the merging clusters can be an ideal local counterparts of the galaxy clusters that will be observed and searched by Euclid, by the space mission in general, but in particular by Euclid, because of Euclid we search for galaxy clusters at high redshift, at redshift 0.2, at redshift 2, and then as you can see from this plot, the wave bands of this shows the wave bands, the pass bands of NISP instruments, and these passbands are also, and then we can see also the bands of the VISTA, and the Y and J bands will be covered by Euclid, but the K band is outside this wavelength range. So VISTA will also extend the near bands of observed by Euclid. Then, as I said before, we need also ancillary data to investigate in detail the galaxy properties and the galaxy evolution. So for this sample, we have in the center and outskirts different observations. In the center, we can take advantage from the existing HST data, in particular from 3 surveys, the Clash Treasury Program with PI Mark Postman, the HST Frontier Fields, PI Lotz, and then the Relics Cluster Survey, PI Danko. Also, we have for the core a coverage from the Muse integral field spectroscopy, both GTO and proprietary data. And then for the outskirts, for the optical coverage, as I say, there are Subaru and the VST data, and for near infrared, the G-CAV survey. And for the spectroscopy, we have observation from VLT VMOS and also Omega. And finally, recently two of these 20 clusters were also observed by JWST, in particular in ERAS program, PI Tommaso Treu, and then a second one program with the PI Eros Vanzella. So this plot shows the exposure times in the different bands for all the clusters observed in G-CAV. And after 5 years, in March 2022 were observed the last OBs, and there were also 3 data releases of this data. The first one in 2019, the second one in 2020, and then the last one just in February 2023. The magnitude limits we reach is very deep, so the optical data, the near-infrared data are very deep, and we can reach also M star plus 7, 8 for different clusters, depending on the redshift of the cluster. These show the distribution of the full width at half maximum and the depth for each OB, because the third data release is concentrated on the OBs, the stacked OBs collected during the survey, and in particular the OBs with grade A and B, and also the catalogs of all these OBs. But in the next release, we will also have the quadded and stacked image for each band. So as you can see, the quality of data is very high, with a very good distribution of the full width at half maximum, with a peak around 0.8, 0.9 in different bands, and also the depth of each stacked OB is very deep, is very high. To better understand the quality of this data, I will show in particular few clusters. In particular, this cluster is Abel 2744, which is also observed by JWST, and this is the Vista image, and as you can see, a part of the Vista image, and as you can see, in the center, there's the Viria region of the cluster, and so this is a very extended. This is a zoom in the center region of the Vista image, and then this is a combination, a combined image of optical, Magellan, and also K Birkan band, in particular in the Viria cluster region, and also this is a zoom of the central region of the cluster, where you can see the great variety of galaxies with different properties, with different morphological structures. Also, Abel 2244 was observed by JWST, and in particular by 2 different programs. The one, oh sorry, the one is, oops, okay. The one is the JWST GLASS program, PI Tommaso Treu, and another one is the uncovered program. And then in green are the squares indicating the MUSE coverage of this data. Another cluster that I would like to show you is MAX 0416. This cluster is a higher redshift, and here you can see the VISTA data and also the VST data. This is the coverage obtained by the VLT VMOS spectroscopy, and then also for these clusters we have HST Hubble frontier fields in the center, and also MUSE data. As I already shown, these clusters are also part of the sample observed with VST. So in particular, we observed 6 galaxy clusters that are listed in this table below, and these clusters have a redshift between 0.2 and 0.5, and this is a VST GTO survey of 300 hours, complementing the optical data that were already available for the G-CAV survey. So covering the U, G, R, and I band in a region which reach around 5 times the virial radius. Also for this survey, we are able to observe galaxies up to 10 to 9 solar masses, so in a region where the model predictions are in agreement with the data, in particular for the tension with the number of the dwarf galaxies. Also, as the image that's already shown, these are the clusters in the semi-identical models covering the 20 per 20 parsec as the field of view of VST, and then in the center there's the region observed by Subaru, 30 per 30 the arc mean, and then also, as in the previous slide, these are the clusters at redshift 0.3, and in red the central galaxies, and in blue the satellite galaxies. MAX 0416 was also studied thanks to the spectroscopic coverage by one of the work on the galaxy evolution that we already published. So as an example, I will show the results of this work to better explain the potentiality of the VISTA data combined with all the ancillary data. In particular, we obtained 900 spectroscopic members, but with the VST and the VISTA data, we derived photometric redshifts, and in particular, we obtained a photometric redshift with an NMAD of 0.04, so quite accurate photometric redshift. And thanks to this redshift, we were able to, I don't know if, okay. Okay, sure. Okay. This is the density. This is the density map at a different redshift, in different slides at different redshift. And so we select the photometric members to complete and complement our spectroscopic sample to investigate also the galaxy properties in the filaments, in the filamentary structure of the cluster. So this can show you the density field of the selected about 5,000 galaxy members, 4,000 plus photometrically selected members, plus 1,000 spectroscopically selected members. And then you can see the very huge structure of the clusters with other two substructures that are outside 5 virial radii. In particular, we also select the red sequence galaxies to have a higher contrast of the structure, and we selected 1,030 about 400 galaxy clusters belonging to the red sequence. And with this sample, we again evaluate the density field, and you can see that the main structure of the cluster is highlighted. But also there are two very concentrated substructures, and we would like to investigate the processes, the properties of galaxies in these two separate substructures, and also the properties of galaxies in the filament that seems to connect these different three structures. Performing this analysis, so we just selected the galaxies in the very high density cluster core, and also in the high density region of these three substructures, and we compared the properties, in particular the colors, at this stage of these galaxies compared to the cluster structure. And as you can see, we see almost similar properties of all the galaxies in the T structures. But this data will be also complemented with our omega spectra, so we try to confirm our suggestion that the pre-processing processes are very important in transforming in transforming the galaxy properties, in setting the galaxy properties. Then, by comparing also galaxies belonging to different density regions, we have seen that as expected, the red sequence, the colors of galaxies is different in these regions, and also the galaxies are bluer in the low density region than in higher density region, as we expect. So finally, this study is just to show you the potentiality of this this VISTA data. And so finally, I would like to summarize the G-CAV survey, which is an unprecedented near-infrared wide area survey for 20 galaxy clusters at intermediate redshift, covering a total of 300 square degrees in Y, J, and K bands, and is, together with the other optical ancillary data, is an ideal survey to study the nature versus nurture processes in galaxy evolution. So this very huge field of view of VISTA also sample a wide dynamical range in density and also in properties of galaxies, and this depth and area will result in an important legacy science to observe to search for quasars and dwarfs. And also for this survey, the data release 3 contains the all OB stacked images and also the photometrically and astrometrically calibrated, and also the catalog for these OBs. And this is the link for to download the data. So now we are completing the Marius work, and with the DR4, we will include the full calibrated stacks in terms of images and also all the catalogs for these images. And so, thank you.